Have you ever wondered about the invisible forces that are powering, well, everything? From your phone to spacecraft way out in the cosmos. In this explainer, we're going to pull back the curtain on one of the most fundamental concepts in all of physics.
Okay, check this out. What you're looking at is an ion engine. And that faint blue glow, that's not a chemical explosion like you'd see in a traditional rocket. Nope, that's a spacecraft being pushed along by a force you can't even see.
So how in the world do you move something with an invisible force? The answer lies in this really cool concept, an invisible landscape made of energy. To understand how that ion engine works, we first need to get a handle on this landscape.
So first up, let's talk about gravity's energy landscape. We'll start with something we can all wrap our heads around, something we experience every single day: gravity.
Just imagine a ball sitting right at the top of a hill. It's packed with what we call gravitational potential energy. It's unstable, and with just a little nudge, what happens? It naturally rolls all the way to the bottom, where it's stable and its potential energy is at its lowest.
And that's the key right there. Things just naturally want to move from a state of higher potential energy to a state of lower potential energy. This one simple rule creates a predictable energy landscape that governs so much of our physical world.
Okay, so we've got the idea of an energy landscape with gravity. Now, here's where it gets really interesting. We can take that exact same idea and apply it to the world of electricity.
So just like a ball has potential energy because of its height in a gravitational field, an electric charge has potential energy simply because of where it is in an electric field. You see? It's the same core principle. We're just dealing with different players.
So the crucial takeaway is this. The roles that mass and height play in gravity, they're mirrored perfectly by charge and position in the world of electricity.
Now, what's really fascinating is how this landscape actually changes depending on the charges. For example, if you have two positive charges, they create an energy hill. To get another positive charge close, you literally have to push it uphill against that force. But with opposite charges, they create an energy valley, and they just naturally fall into it together.
But what if we want a map of this landscape itself, without having to drop a little test charge everywhere to see what happens?
Well, that map is exactly what voltage is. It's a chart of the potential energy that's just waiting there at any given point in an electric field. This gives us a really concrete unit for our energy map. 1 volt just means there's 1 joule of energy available for every coulomb of charge you place at that spot. So a higher voltage means a steeper hill on our landscape, with a lot more potential energy ready to go.
And here's a perfect real-world example. A simple battery. It maintains a constant voltage, a potential difference, between its two terminals. What it's really doing is creating a reliable, stable, electric hill that's always ready to push charges through a circuit. So why does all this matter? I mean, who cares about invisible hills? Well, you should. Because harnessing this energy landscape is the key to pretty much all of modern technology.
Okay, let's go all the way back to our ion engine. Now we get it, right? The engine creates a massive potential difference, a super steep energy hill. Then it places charged ions at the very top of that hill. And they do what comes naturally. They roll down it, accelerating to incredible speeds and shooting out the back to create thrust.
And you don't even have to go to space to see this. We see this same principle at work right here on Earth. Welding creates such a high voltage that it gives charges enough energy to literally leap across an air gap, generating immense heat that melts metal. So, this invisible landscape of energy isn't just some concept in a physics textbook. It is all around us. It's powering the technology in your hands right now, and it's shaping the entire universe. So I'll leave you with this thought. If voltage is an energy map, what kind of incredible journey are the charges taking inside the device you're using to watch this? This invisible landscape is everywhere. The only real question is, where will you see it next?